everybody. I'm Javier. I'm professor at Polytechnical University of Madrid. I work in the group of research group on quantum information and quantum communications in UPM. And the idea of this talk is to give you an overview of the things that are happening in Madrid with the Madrid Quantum Communication Infrastructure, which is the beginning of this. And as you can imagine, this is a wide open thing because there are too many things happening there. So I tried to select some interesting use cases and ideas that we have. So I will present you this. Okay. So of course, please interrupt me any moment to questions or whatever. So I'm not going to go in the full details of everything. Okay. I'm going to give you an overview, but if you are interested more in some aspects, I will tell you. Also, this work is done by all those people. Now, I think that we are even more. Okay. So yeah, this is our group, and then the talk will be will be a table of contents. First, I'm going to talk about quantum key distribution in theory and practice. In theory, probably I will go fast because you know a lot of things now. Then we are going to move to quantum networks, and then I'm going to motivate you a little bit some aspects of post-quantum cryptography and the hybridization with quantum keys, let's say, and post-quantum keys. And then I'm going to present you a selection of use cases or concepts, proof of concepts, and ideas that we have to do with MadQCI, from things that we are doing and are more in the ground, let's say, to more futuristic things. Okay. So, in theory, quantum cryptography. Quantum cryptography is, in principle, is any means of doing cryptography based on the processing of quantum signals, with the processing and transmission of quantum signals. We typically think as a quantum signal the qubit, and this is true, but in general, there are more quantum signals that you can use. For example, these coherent states, you can use it for doing cryptography. They are not qubits, okay, let's say. So yeah, this is in principle what we mean by quantum cryptography, and usually this quantum cryptography is equated to quantum key distribution. One thing that is important is that quantum key distribution is not to, let's say, distribute keys created by quantum mechanics. It's growing keys in the endpoints through a protocol that involves quantum mechanics. So, under my opinion, it's more accurate to think of it as quantum key growing, because you use that quantum signal to extract some information, and then with this information processing, and then extract your quantum keys. And also, there are other algorithms that you can execute using quantum signals, such as Oliver's transfer, circuit sharing, and they do not necessarily share the same security properties. Okay, I will introduce you a little bit Oliver's transfer, and the security properties are not the same because the purpose of the algorithm is not the same. So, I mean, I will talk a lot about quantum key distribution, but quantum cryptography is more than quantum key distribution, right? And the typical protocol is BB84. So I'm going to skip this, okay, because I assume that you know, if you have, for example, in polarization, vertically polarized photons, if you measure this, all photons will give you this state. This is orthogonal, so no photon pass. And then if you do a measurement in the Hadamard basis, then some photons pass or no, and you will obtain this result. So this is essentially to play in discrete variables with the Hadamard basis, the rectilinear basis, and this is our game, let's say. So BBT4, what it is? Alice choose one of the 4 possible photons with a basis and a value of the bit. She sent the photon, then Bob measures in a random basis. And in this case, for example, he used the correct basis. So they obtain the correct result, and they repeat this again and again and again. Okay? For example, in this case, Alice sent the diagonal photon, a diagonal Paris photon, but Bob did the wrong measurement, so he obtained with a 50% chance a wrong result. So they repeat all of these. Okay, I'm going to skip this because I assume that you are familiar with this. And then in the next phase, Bob shares the results, the basis, the measurement basis with Alice. Alice then checks what are the same that she prepared, communicates to Bob, and then they keep the ones that are the good photons, the good measurement. So they obtain a symmetric. This is BBT4, and if Bob or Alice see that the symmetric key is not equal, there are at least one bit that is different, then this is because there is a eavesdropper in the middle, so they abort the communication. This is the idea. And why they know that there is an eavesdropper? Because they sacrifice part of the key that they have to check if there is some bit that is different. Okay, this is in theory, everything. This is the original paper of Bennett Brassard in the 1984. You see here that the control mission, Alice emits, this is an example of this information. Bob receives this. This is called public discussion, the classical part is called public discussion. Here you have the error correction, and then distill this key. From all this information, they get this key. So this is what I said before. I mean, those photons are not information, are the material, the quantum states from which I distill a key with some protocol. So after the qubit detection at Bob's side, what we have is the raw key. The raw key may seem trivial with BBT4, but it's not easy to define what is a raw key in general for multiple protocols. Okay, because for example, in this case, the raw key is all the information that Alice and Bob have, such that if they exchange that information, they can distill a symmetric key. So in this case, for example, will be from Alice's part, the basis and the basis that she used and the value of the bits, and from Bob's side, the basis that he used to measure and the results. This will be the raw key for BBT4. And this is asymmetric. This is a symmetric key. So with this raw key, Alice and Bob needs to process this key to obtain the final secret key. And this involves those steps: sifting, error correction, private simplification, and authentication. In the theoretical world, it is enough with these two steps, sifting and error correction. Okay, because I mean, if they sift the key, they keep the good, let's say, bits, and then share a part of the key. If there is only one error, they know that there is an eavesdropper. But in the real life, errors come from if and the environment. In reality, the environment raise the same role as an eavesdropper. Okay, so we have to distinguish between the environment and an eavesdropper. So we have to perform additional post-processing. So the first thing is the raw key extraction and sifting. So using the public channel, as I've said, the emitter publishes the basis in which the qubits were prepared. This doesn't have to be encrypted, but it is important that I'm saying that this channel should be authenticated. Okay, you are familiarized with digital signatures. Do you know what are digital signatures? How many of you know what is a digital signature? Okay, I will explain to you later in one use case that I'm going to present. But here the idea is that when Bob, for example, communicates to Aris those bases to extract the key, Bob needs to know that you are Aris, because if you are Eve, we are not communicating. I mean, you cannot extract information because this is public information, but I'm not communicating with Bob. Okay, so this channel should be authenticated, and to authenticate this channel, I have some methods. One method is to use classical cryptography. The digital signature algorithm, which is based on public-private, on asymmetric keys, and this is not quantum resistant. So here we have a problem. Other method is to use pre-share key. When you buy a device, a QKD device, inside there is some pre-share key from the vendor, and then you put Aris there, Bob there. Initially, they talk to each other, and they authenticate with this pre-share key. And from this moment, they use the key that they are growing, to authenticate for further sessions. So this is another method. And many people will tell you what happens if you lose this pre-share key somehow. Then you cannot communicate, you cannot authenticate. Okay? The third method to authenticate is to use post-quantum cryptography. How many of you are familiar with How many of you know post-quantum cryptography? Okay. So post-quantum cryptography is a set of algorithms that, in principle, we don't have demonstration, but in principle, are resistant to the attacks of a quantum computer. Okay, and they are classical protocols, not quantum. We don't have a proof of this quantum resistant, but we believe that are quantum resistant. Okay. I will talk about this later. So they use this public channel to sift the key. So they select the correct bits, and then they start the error correction. Error correction. So in practice, errors come from if and from the environment. So you have to calibrate this channel with environment, and then you can distinguish between the environment, the noise, and if. So this quantity, the number of errors versus the total number of bits, is the quantum bit error rate, QBER, and this is a critical number because it's closely related to the amount of key that I can extract from the amount of bytes per second that I can extract from a pair of devices. Okay. So once Aris and Bob sacrifice a part of the key, and they know that there is no if, okay, they start correcting the errors that they have in the keys that should be perfect, but they are not. So there are some protocols, some classical protocols to correct those errors. Cascade, for example, is a very common. which Cascade basically divides the bit string in blocks, and then Alice and Bob share the parity of these blocks. So if the errors are moderate, they can correct through this parity the keys. Okay, but they are revealing some information, because this parity, or the parity of these blocks, are transmitted through a public channel and it's not encrypted. Okay, so if knows this information, so well, this will this information will be this information from it will be corrected, let's say, in the private simplification, but for you to have some numbers in your head, the quantum bit error rate gives the limit in when a secret key can be extracted, and for example, a very good quantum bit error rate is 1%. Okay, this is a very good QR. With 3 and 4%, you obtain high Q rates. Beyond this threshold, the secret key is reduced, and the theoretical limit is 11%. Okay, so we play with those numbers. Let's say 1 to 7% of quantum bit error rate to have devices that work. Okay, that do something. Of course, this limit will depend on the protocol and the assumptions. And for example, in continuous variables, we work with extremely high error rates. So the error correction part is very demanding there. Okay. Because of this information that has been shared in this error correction phase, we have to perform private simplification. So private simplification, with this step, we try to eliminate the information that it has about the things that we share, the information that we share in the quantum error, in the error correction. So for example, if an eavesdropper knows that the value of bit 15 is something, but not the 16, then if I XOR those 2 bits, then if won't know nothing about this common value. Okay, and an intermediate case, if the spy knows those values with a 60, for example, % of probability, then if we XOR those bits, the probability of this spy to succeed in guessing this value is the probability of have both values correct, or the probability of having those values wrong, because I'm doing an XOR. Okay, so with this example, you obtain this number, which is less than the 60% original. So this is the purpose of private simplification, to reduce this probability that comes from the information that we share to do quantum error correction. In practice, this private simplification can be done, for example, with hash functions. Hash functions are believed to be quantum resistant, but in this case, it doesn't matter, because we are using only to mix everything and to let's say, obscure this probability of guessing the bits. And this private simplification is possible if the mutual information between Alice and Bob is larger than the mutual information between Alice and the spy, or Bob and the spy. So you have this famous plot in which you have here the quantum bit error rate and the information per bit. And in this regime, until here, which is the theoretical limit, which is this, I don't know with the protocol, I think, no, this is the 11%, okay? You have this this regime in which you can extract secret key. From here, you cannot extract secret key, because from here you can extract secret key, and here you cannot even do private simplification. Okay. So this is the theory of QKD. Now, what happens in practice? Okay, in practice, you need a quantum channel, you need single quantum detectors. If we are doing DV, in CV, not, but in principle, you need to detect these quantum signals. You need emitters, and you need to be able to prepare and analyze these results. So the first problem that we face is that you have to transmit a single quantum from Alice to Bob. This is a typical signal, a laser signal, a communication signal. Those are the typical signals that are going through the fiber in classical communications. And this is the signal of single photon, and it is not in scale. I mean, it's even much lower. I put this bigger because if not, you won't be able to see, okay, the signal. So this is the first problem, okay? The signals are obviously extremely weak. A single pulse can have 10 to the 8 photons, but we want 1 photon. So this is the first problem. Other problem is that signals are always absorbed, okay? If we have perfect vacuum, no, but this is not the case because typically we transmit signals through the fiber, so the signals are absorbed. And you can say, okay, and what if you throw your quantum signals to the air? Because the air is much close to the vacuum than the fiber. You have other problem here, which is the aperture of the laser. If you have a laser through the air, the laser will is not perfectly rectilinear. Let's say the laser have the laser have an aperture, and this becomes very critical for long distances. Even for not so long distances, but you have this problem. So you have here this figure in which you can see the distance and the key length of the structure key from a device. So you see how this is logarithmic scale. So you see how there is a critical distance here from which further away I cannot extract key no more. Okay, you have here some numbers. If I have a source with, for example, 10 to the 9 photons per second, then in 50 kilometers I have a lot of photons, but you see that this decays, and for example in this 300 kilometers I have 1,000 photons that are a very low amount of photons, taking into account that I have initially 10 to the 9. But for example, you see that those distances are not possible, because here I obtain 1 photon per 20 minutes, and here 1 photon per 36 years. So there is a boundary there in the distance because the absorption. And moreover, I have the interaction with an environment that can cause not absorption but decoherence. I mean, the quantum signals may suffer some decoherence through the path. So I have those 2 problems. And I have another problem with the transmission line. Okay, that is everything. This is everything that I've said here is for let's say a fiber in which I don't have any signals. Okay, I don't have classical signals. I only have my photons. What if I have to share this fiber, which is the typical scenario, to do quantum communications? You have another problem, which is the Raman noise, Raman scattering. Okay, so the Raman scattering is the inelastic scattering of the light with the medium. So this means that if I have, for example, here a laser emitting in this wavelength, which is the C band, the the typical wavelength of telecommunications, then I will have all this noise in all these channels, in all these wavelengths, okay, because of this Raman scattering. What is the problem here? The problem is that I have to measure things like this, that are very low with respect to the noise. This is more or less a single photon. So this crosstalk is very difficult to avoid when you have to coexist quantum signals with classical signals. And even you can say, okay, so you can go far away from this and then you do your quantum stuff. But the current trends in classical communications in the physical layer is put as many channels as possible in a single fiber. So here you can see let's say the life in the optical fiber, and you see that this is the attenuation and this is the wavelength, and then all of this is occupied. Okay. All the people is emitting light in those channels, in those wavelengths. If you go there, you don't obtain advantage because you have a lot of attenuation, a lot. You have to take into account that the dBs, this is how we measure the attenuation, is a logarithmic scale. So I think that 2 dBs is doubling. Okay. So yeah, no, 3 dBs is doubling. So you have here, this is impractical, and this is occupied. So you have a problem. Raman scattering is a problem. Okay. We have all the problems in the, for example, in the detectors. Okay, we have various types of detections: superconducting detectors or solid-state detectors. The superconducting detectors are good. They have a low dark count, which is the amount of clicks, let's say, amount of detection, fake detections that happen when there is nothing. But they work obviously at very low temperature, and they are very bulky. Okay, the solid state, they do not require this bulky cryogenics, but they are not so efficient. You have after pulses, so you have here problems. A convenient way to measure quantum signals is the homodate detection that you know very well now. This is very convenient. It's telco-friendly because you don't need these fancy things, okay, to measure, but it's only compatible with CB protocols. And those photons are very difficult to produce. You don't have single photons at demand. Typically, you use an attenuated laser to produce these photons. Okay, so you have to load the mean number of photons, so you can have photons more or less in a regular rate, but you minimize the probability of having 2 or more photons. So you have here a threshold, and then you have to, of course, you cannot put here 0, because if you put 0, you obtain the vacuum state always. So you have to calibrate a little bit this to have a good, let's say, performance, but to avoid double photons events or more. So this is not, let's say, the thing that we want, but it is what we have. However, in spite of these problems, it is still possible to do quantum key distribution in practice. And this is, I don't know if you have seen this picture before, but this is the first QKD in the world. Okay, it did implementation in 1989. Okay, and was the channel was 20 centimeters. I mean, it's a proof of concept. And then you have here, yeah, but it's very simple. I mean, you have here the laser source, the polarizer, the quantum channel, and Bob is the receiver. One funny thing about this experiment is that when the polarizer was working, this emits sounds. this sound is related to the basis polarization. So just listening to this sound, you can get the key. Okay, so it's not very practical, but it was the first implementation of BB84, and with this experiment, it has been demonstrated that it is possible to do quantum communications. 20 centimeters, okay, but this is possible. There are protocols that improve the points discussed earlier, such as continuous variables. So, for example, the main advantage of those continuous variable protocols is that you avoid to use expensive, strange components, and you can work only with lasers and beam splitters and more or less this. Okay. So I'm going to skip this because you already know this. Okay, you work here with the quadratures of the light, and you work with this uncertainty principle here, in which you cannot distinguish exactly the states. And then you have these nice experimental setups that are very telecommunication friendly. So this detection method is less affected by the Raman noise, okay? Because you are performing an interference between two signals. Okay, so it's less. You don't have to detect one single photon that is mixed with all the photons. You are measuring an interference, so it's less. It's affected, but at less. You don't need this fancy stuff such as single photon detectors. You have better industrialization possibilities and it's cheaper. But the drawbacks is that the post-processing of the signal is very heavy. And in general, DV reaches more distance in general, okay? Because it's less affected by the losses. Okay, this is QKD in practice, and now we are going to move to quantum networks. Okay, how do we mix all of this to create a quantum network? Okay, we have this negative thing, which is the limited distance, okay, the losses. So we need trusted nodes. Okay, if I want to communicate I want to perform a long distance communication, I will need in the middle nodes that gets the key and presents the key with other quantum key to the next node. Those nodes should be trusted, which mean what means trusted? In these nodes, the key will be unencrypted and encrypted again. So I need to trust on these nodes. You have low tolerance to noise. You have these quantum and classical propagation issues. And not sharing the infrastructure is extremely expensive. It's not practical. Okay? You have to share the infrastructure with classical communications. And then you have this alien technology, both in hardware and software. So all of this does not play well with classical networks. Okay. So what can we do? There are two possibilities here. Well, there is one possibility only, but in principle there are two possibilities. You can build a Haddock network, a Haddock QKD network, just for quantum. Okay? Or you can integrate the quantum network through the SDN paradigm. Okay? So first, before going through these options, we are going to take a look we are going to take a look to layer networks, okay, to classical layer networks. So this is the OSI model. How many of you are familiar with this model? Okay. Okay. So this is actually the model in the present for classical networks. Okay. This is a layer network. This means that the functionalities of the network are constructed, are built in a layer form. So, for example, you have here an analogy of this distribution of functionalities, which is, for example, the application part is the manager that wants to send a message. Then you have those two layers that are in charge of give the correct format and to pass this information to the driver, let's say, which is the transport layer. This is an important layer. That goes to the post office. Okay. Here you are in the network layer, and then in the network layer, the post office don't care about the message, but care about how to send the message from A to B. So you have to establish a connection. You have to talk to the physical link, and in the physical link, you transmit the bits. Okay, and then you, let's say, decapsulate all of this to the application that is in the other side. So this is kind of a classification of a division on the functionalities of a network. So we have things in boxes, independent boxes, and when this guy wants to talk with this guy, I mean, he cannot talk with this guy. He has to talk with this. So we keep the modularity of the functionalities of the network. Here you have a lot of protocols that you probably heard. HTTP, for example, is in the application layer. SSH is in the application layer. Okay. Then you have, for example, these protocols related to some formats, RC, MPEG. You have here IPsec, Internet Key Exchange, okay, which is when you want to communicate to a server and you establish some private and public keys to communicate, some common secret to communicate. In this layer, you have the Ethernet, the Wi-Fi, and here you have more physical layers, physical protocols, or standard, for example, the USB. USB is part of the physical layer of the network, which is how physical things have to be built to connect with other. So you have all the things that encompasses a network here. In this is the OSI model for classical networks. Okay, so when talking about data, this works with headers. Okay, for example, you have here the user data, which is the message that this guy wants to send to this guy. Okay, and then when you go down to the lower layers, you add, let's say, some headers or some trailers. Okay. For example, here you have the application header, then the TCP header, which has to do with this transport layer. Then you have the IP layer, the header. For example, the IP header is related to the IP address of your devices. So, for example, with the IP header, this packet, when it goes through a router, the router knows where to send the packet. Okay. So you add this information through headers to your message, let's say, to your the thing that you want to communicate, and then you, when this reaches the destination or other parts of the protocol, then encapsulate this and you obtain the user data. So this is kind of a Matryoshka-like behavior, but this unpacking idea does not exist in a quantum key distribution network, okay? Because there is no packing for photons. I mean, the photons themselves are the raw material that generates the circuit bits, okay? So we can try to adapt this model and to understand a little bit this thing of layering in networks. I have one example that I like a lot, which is the washing machine example. Okay. So, okay. Imagine that you have a washing machine. Okay. So you can say that, okay, in order to wash my clothes, I need something to put my clothes on, and then I need some soap. I put my clothes here. This thing starts to doing things to rotate and so on, and the clothes are washed. Okay, this is the idea. However, I wouldn't say that this is a washing machine, only a pot and soap. This is not a washing machine. I need some controls here to say, okay, please rotate at some velocity. Please put more soap. Please put more water. 10 liters of water. Some milliliters of soap. So those are the, let's say, this will be the management plane, let's say. This will be the physical plane. Okay. So this plane, when I put this this dial, for example, to 50 to a velocity of 50 rounds per second, then this starts to rotate at 50, for example. And when here I put 10 liters, then the mechanism, the physical mechanism, will give 10 liters of water. Okay, so I need this, let's say, management plane, so I don't care about the physical stuff. But so what if I want to, for example, wash my my dark clothes or my white clothes, for example, or some delicate clothes? You hear in your washing machines, you have here some programs that you press the button, you see the time, and then the machine do the work. So this is the control plane. So the control plane, in this case, talks to the buttons, and the buttons talks to the physical plane. This is kind of an example of this layering in quantum networks. That for me, it works very well. Okay. With this layer networks in mind, the first approach is to build a Haddock quantum key distribution network. So this will be the physical layer, the quantum plane, okay, in which you have here quantum key devices, okay. You have quantum channels, you have classical channels, and then here is where the emission and detection of quantum signals happen, okay. Then you have other plane in which you process this information to get keys. Then you have other plane, which is the key management plane, in which you manage the keys somehow. And then you will have this application plane in which you have your computer and you do all your things, okay? The services feed from the keys from the key storages that are here, and those key storages are fed using these quantum key connections. This is an approach for quantum networks. This is the approach of quantum networks that build with the things that we have today, with the theory of network that we have today, we build a quantum network. Here we have some problems. If you are building, the first problem is you are building this. So you are, this is extremely expensive, okay, to build Haddock networks, only for this. That does not coexist with other protocols, other classical stuff that is happening. Okay, this is extremely expensive. It is not integrated with existing telco networks. This is difficult to deploy because it's non-incremental. If you those routers, for example, work as the routers that we have. Those from here to here, the elements are the elements that we have nowadays. So what happens, for example, if this link doesn't give me the key rate that I need? I have to reroute those things. What happens if I add another QKD device, another node? I have to take into account all the structure of the network to optimally construct this node. So this is not incremental, it's not modular, okay? And here you are facing with very high upfront costs. So this means that there is no pre-existing large market to create it, and you cannot create it because there is no pre-existing large market. So you have here a kind of a bottleneck here. You cannot do this because there is nothing done in this direction. Okay. The goal is that, yeah, you will have, if you build this ad hoc network, you will have a high performance for QKD, but it's not realistic. Okay. The network model that works for QKD is the SDN model. How many of you know the software-defined networks? Okay. Look at this, the washing machine. This is not a SDN washing machine. Okay. The SDN consists on two things. First, to decouple this control plane from in the case of the networks, the data plane, which is more or less this management plane, these buttons over there, to decouple these planes, which is seen in this example is done, but in general in networks is not necessarily done. Okay, you have to decouple this, and then there is other thing that you have to do in order to create an SDN network, and it's the following. In this example, you have in the control plane. In the control plane, you have these pre-existing programs. Okay, the SDN and SDN washing machine is the one that doesn't have those programs, but here you have a programming language, a syntaxis, and a way to program the things that you want. So you can create a program, put it here, and then this will do the things. Okay. This is a programmable washing machine. The SDN network is a programmable network. Okay. You need that the control plane have a syntaxis, a programmability, so you can write, let's say, code, if you want, the things that the control plane should do. Okay, this is SDN. It's not only decoupling, because if you go to literature and all the people say that SDN is to decouple the data plane from the control plane. True, but it's more than this. It's to be able to program this control plane through a language. What does it mean? It means that this network, this classical network equipment that are black boxes, okay, now are open interfaces. I can tell those, for example, the routers, what are the routing, what is the routing table, for example, dynamically, okay, and all the same for all this network equipment, okay. These boxes with autonomous behavior that operates in a network, in SDN, those decisions that takes those boxes are taken out of these boxes. Okay, so the idea is to create devices, stupid devices, and to transfer all the intelligence to a manager, to an upper manager, okay, that controls all the network. So this is SDN, to have the ability to program this. So why this fits? Why SDN fits with quantum key distribution? Well, for example, in QKD, if the SDN paradigm solves all these, for example, all these problems, okay? How can you route keys across multiple hops? With SDN, you have a global view of of the network, so you can dynamically change this routing. Okay, what happens if a path is one link is degraded? You can take this into account through a smart, let's say, controller of the network. Okay, because it's programmable. How you allocate these key pools to multiple applications? You can decide it dynamically. Okay. How do you orchestrate different devices from different vendors? Because in practice, you have a lot of vendors that, in principle, nowadays no, but in principle, they may give you, for example, the key or information in a non-standard way. So SDN can abstract this heterogeneity from the devices, so you don't care about the device, okay? Because you have common interfaces. And the more important thing is that telcos, telecommunication engineers, know SDN. So this is not new. This is not something that that came from quantum key distribution. This is something that was proposed a long time ago. So people know these software-defined networks. So QKD can be easily integrated. Okay. Of course, if you want to improve to make a large network, you need more QKD devices. But this paradigm of SDN help you to do it in a scalable way. But there is more, because SDN is an enabler of QKD, but SDN is a consumer of QKD in the sense that new challenges are created with adapting QKD, using software-defined networks to create QKD networks. For example, all this softwareization that is needed to create this software-defined QKD network poses new security challenges, okay? Because I need to ensure the communication with the controller, with the agent, and so on. So, I mean, SDN and QKD are a good couple, because SDN is both an enabler and a very good use case of quantum key distribution. With this in mind, we started to work on this in 2029, this year, with this small network. Okay, then 5 years later, grow to this with Telefonica, and this is the layout of the 2018 iteration of the Madrid SDN QKD network. This is Madrid. Okay, you see that we have 1, 2, 3 nodes only. Central Norte, Central Almagro, and Concepción, and you have here the distance. Okay, 5 kilometers, 4 kilometers, more or less, 6.5 kilometers. Okay, and the attenuation. This network was the first SDN quantum network in the world, and was installed in the production facilities of Telefonica. Okay. This network is this one here, of this iteration, which is the iteration of the network in 2023. Okay. Here you have you see that you have more complexity. We have a bunch of new nodes. We have different protocols running: discrete variable, continuous variable. For example, here you have 2 and 2, 2 and 2. You have only here 1 continuous variable. So it's a very heterogeneous network from different vendors. I mean, the quantum key, the QKD devices are from different vendors, and they are integrated through the SDN in this network. You have switches. You have different levels of encryption. This is when you have the keys, you have to encrypt the data. So you can do it in different levels. Level 1 is the physical layer level. You encrypt directly the thing that is going out from your computer. You have level 2 encryption, which is a network level, so you have different levels depending on the OSI model. And yeah, this is the previous iteration of the network with respect to the present network. This is a picture of what is a node. Okay, there is a lot of cables here. There is a lot of stuff. For example, you have well, here you have the QQT devices. Okay, this one and this one are two EDQ discrete variable quantum key devices in the C band, and which is this wavelength, and the O band with this one. Okay, those are the devices are more or less like this. Okay, this dimension is like this more or less. Then on top you have this optical transfer management and link encryptor. You have the SDN server, which contains all the logic of the SDN. I'm going to give you now a picture of the architecture of the SDN. Here you have the OAD and a programmer switch that will add and drop quantum channels, and you have a Roland Schwartz level 2 encryptor. So this is what a node looks like. Okay. Okay. And this is a diagram of what is a node in the SDN paradigm. Okay. So here you have the quantum key distribution system. You can have 3, 4, 5, a bunch of quantum key systems or quantum key distribution modules. And these systems that are those guys over there, okay, the devices, talk to this guy, which is the local key, local KMS, local key management system. And the keys, the quantum keys, go from these modules, these systems to this one. So this key management system is in charge of managing the keys that comes from various devices. Okay, this is very complex because you have to, for example, be synchronized with other key management systems to track which bit is for which in each position, for example, and you have to manage multiple sources of quantum keys. Okay, this module talk with application, of course. The key of the key management system is consumed through the application, and also this module talks with the SDN agent. The SDN agent is the responsible to talk to the controller and to establish to request connections to other nodes. Okay, so the local KMS talks with the agent with some key statistics or key requirements. Okay, but it's the SDN agent which talks to the local KMS, and then the SDN agent, if he wants to open a connection with some other agent, he talks to the controller. The controller is in charge of create this connection. All those communications between all these modules are done by standardized interfaces. For example, here to talk with the between the agent and the controller, you use the 015, which is an interface that defines the interface between for software-defined networks, and you use known technologies such as OpenFlow, which allows decentralized SDN to let the controller forward tables of the switches or routers. Or you have, for example, netconf, which is a protocol that provides a structured way to write and read configuration data of a device. So the point here is that this is familiar to networking people. Okay, and under this point of view, the only quantum thing is this one. Okay, so you only have to put here a quantum system, and then everything is classical and known. This is SDN, and this is not how the classical communications work. I mean, because they are not in general SDN, but it's something that is known. Okay, and this is with this SDN paradigm. You have here a picture of how a SDN network look like. This you have a bunch of SDN nodes. All the SDN nodes are connected to a SDN controller, and each SDN node has this structure, okay, which is the previous structure. This architecture allows you to create dynamic connections and is completely integrated with classical networks, okay, because this is classical. Without this is classical. So I'm going to talk a little bit about each piece, okay? You have the SDN controller, the agent, and the local KMS. The controller is going to control simultaneously the quantum and classical resources in the network. So, for example, the controller will compute the path, the optical path for a quantum channel with, for example, using this or this. Well, this is no, yeah, this or this, for example. This topology application collects info about the topology, and this path computation is an algorithm that you use to compute the paths. Okay, this is happening in the controller. Okay, the path computation and the graphical user interface is out of the controller, but is directly connected. Okay. Okay, so you have the controller, you have the SDN agent, which manages the interactions in the node with the manages interaction between the controller and the QKD modules. Okay, it's based on the quantum abstraction interface and the quantum abstraction module. Okay, this is the minimal set of communications with the quantum key distribution device to integrate this easily, and this the quantum abstraction module translate the SDN control commands, those here, into commands that a QKD device can understand. Okay, and this is done by standardized interfaces, so it's easy to deploy and easy to extend. You have the local key management system that manage the keys extracted from the device and handle it to the application, and keep statistics of the quality of service, okay, which is the quality of the keys, let's say, and uses, again, another important interface, standardized interface, which is the 004, to talk with this guy, with the quantum key module. So yeah, the point here is that all components are large enough, let's say, to be manufactured separately. So you have here modularity, disaggregation, and you use trusted technologies that are known in telecommunication environments. So it's a good approach to create the SDN paradigm is a good approach to create a quantum key distribution network. Okay, this is the message, and this is the network nowadays. Okay. It's a little bit messy, okay, because we have 29 locations, 29 nodes. We have 19 institutions that participate in the network. The network in kilometers of fiber are 700. Well, only the part of Madrid and UPN that are the largest parts of the network. We have 32 quantum systems, 23 QKDs, and 9 QRNGs. From 10 different vendors. I think that we have all the vendors, more or less. Maybe one or two are not. But we bought quantum key devices from all the networks. For all the vendors. So it's very heterogeneous. Okay, and it's built with under let's say different scenarios. Okay, I'm going to you can go to this link. Okay, I'm going to show you. Well, here. Okay. You have, if you click on this link, you have this interactive map of the quantum network. This is Madrid. Okay, and for example, if you click here, you see the UPN part of the network. This is more or less the first, well, it's not the first, but more or less, this is the first iteration of the network. Then we have extended here. Here we have our laboratory. Okay, this is the campus. We have a ring here for do some switching things. And, oops, yeah, you can, for example, add to see what's the part of Red Madrid, which is another an institution that is in charge of the optical infrastructure of the universities, okay, in Madrid. So here, for example, the important thing is that you have here two different domains. Okay, so those two different, they're not different networks, but they're different domains. Oops, here are, for example, connected through this node, which is called Rectorado. Okay, and then you can, for example, have the domain of Telefonica, which is a triangle here. Indra, which is another company in green there. I mean, it's very, we have a lot of nodes. And then the network is structured in scenarios. Okay, we have for example, the so-called the main scenario in which we run some use cases. Okay, is this one here, which has some properties. Then, for example, you have the demonstration scenario, the hybridization, in which I will tell you later, but we run beyond QKD or hybrid experiments, use cases. The switching scenario that is very small compared with the other ones, but it's interesting because we have this ring and we can control very well the attenuation and those things. And here we are more interested in what happens when you switch and the paths, these kind of things. And then we have other interesting scenario, which is the high security scenario. Where are you? Here. And the particularity of this scenario is that the nodes are the military nodes. So it's very, very complex to convince the military people to put your server in their facilities, the high security facilities. Okay? So this is for running essentially military use cases. Okay, you can go to this link and to see. Okay. And to see a little bit with more detail is the quantum net, the MadQCI. Okay, this is what I just tell you, and yeah, we are a lot of institutions. For example, the ISOM, the Spanish Meteorology Center, the military guys here. I mean, we are a lot of people, and also we are a mix of institutional entities and industrial entities. So it's an extremely heterogeneous network because of the devices, because of the different nodes, because of the institutions, the multi-domain. So we can run a lot of things, a lot of different use cases in this network. Questions here? Yeah.
One thing is with the OSI model, I think the new
OSI model.
Yeah. So the new BCPIP, I think this is the old model. We don't need sandwiches. So you are implementing the old one or the same one?
I'm not sure. I'm not sure. because I think that we are using the new one, the TCP, TCP. Yeah. But yeah, I would say so.
The thing is, the key management is not like how do you secure it? Is it post quantum or because you are doing QKD with the controller?
Yeah.
For security of
no, but the key doesn't go to the controller.
It goes to LKM. The key
management. The local.
It's not a quantum layer; it's a classical layer.
The key, this key is stored with the local key manager, and this inside the node, so it's a trusted thing. You don't need to obscure or encrypt anything.
So it's
kind of a
Ethernet or like internal layer of Ethernet?
No. I mean this. Here, this device gives you the key, and then this is transmitted to here, to the probably through the to the encryptor directly.
If someone attacks the server, he can access this.
Yeah.
Post quantum or like.
This is not secure. I mean, this is not secure. Okay, but. This server is okay. Now I understand your question. Yeah. No, the point is we don't secure this because this server is connected to. I mean, within the server you have several virtual machines that are creating VPNs among them. So it's quite complex to access from. I mean, I'm not an expert on this. Okay. But it's very complex to access from the internet to the internal network. Okay.
And do you have this data set for the amended quantum network? Is it public? Is that the structure of? Is it public? It's available or?
The what? Sorry.
The data set for quantum network that you showed.
The data of quantum.
We have data sets for different classical.
Yeah, I mean, do you mean the data about this
of the network, the topology?
Yeah. I mean, we have. I don't. Maybe I.
Showed it on the Google.
Yeah, we published a paper. I'm not sure
if. Available in the paper.
Yeah.
If I understand correctly, all of the nodes are then only connected at the classical level. Have any of the vendors designed it to try and interact at the quantum level? So two quantum hardware computing nodes could talk to each other?
Two different QKD networks.
So yeah, and it's only better technology.
I mean,
or alternatively, could you have them running on the same multiplex different QKD links on the same network? Kind of one of those two.
This is a good question because this is something that vendors are trying to do. For example, Lux Quanta, which is a QKD vendor from Barcelona, it's a spin-off from ICFO, is starting to do some research on how to multiplex one device to be able to talk to not one Alice on Bob, but for example, one Alice multiple Bobs and things and so on. I mean, in principle, it's not very. It's a switching problem. But the point is that if you have a switching problem, the problem is that you have to calibrate the channel. So you are able to distinguish between the noise and an eavesdropper. And if you, for example, if you have here, I'm one Alice, Bob number 1 and Bob number 2. Then if I want to switch to this Bob, I have to calibrate this channel, and these are 10 minutes. It's not a big issue, but those are 10 minutes. Okay, so and you cannot kind of do it in a you cannot do multiplexation, for example, to do in parallel. I mean, to communicate with you, for example, in time. You cannot do it because you have to calibrate. So, I mean, nowadays, people are working on this, but nowadays, in principle, with the technology nowadays, you cannot communicate multiplexing. Okay, so now I think that I'm going to tell you some use cases that we run in the network. But first, I'm going to remember you a couple of things. Okay, in classical cryptography, in classical asymmetric cryptography, we rely on one-way functions. For example, in Diffie-Hellman, you rely in the discrete logarithmic problem, or in RSA, you rely on the factorization problem. Those are one-way functions. The problem is that there is no mathematical demonstration that when one-way function exists. This is something that we believe because we have a lot of evidence, but we don't have a mathematical demonstration. So with our computers, yeah, okay, this works, and we have a strong evidence that those functions are one-way, but because of the Shor's algorithm, we know that quantum computers are a threat to this. So what is the solution? The solution is quantum key distribution or post-quantum cryptography. Post-quantum cryptography is a kind of cryptography that is based on mathematical problems that we believe that are resistant to quantum computers. Okay, there is no mathematical demonstration, the same as classical cryptography, but we have evidence to believe this. Okay? This evidence, this confidence is done through a standardization process that is led by NIST. Okay? So the NIST, the National Institute of Standards and Technology in the United States, initiated in 2016 a process to standardize post-quantum algorithms. So there was 4 rounds, and then now, from I think 1 year ago, we have those 3 standards: one for encryption, the key exchange, okay, and other 2 for digital signatures. So the criteria to select those algorithms is not only the security, but also the efficiency and the size and other aspects. Okay, and those are based on, for example, those 2 are based on learning with errors, which is a mathematical. I mean, it's a very simple mathematical problem in the sense of the formulation of the problem. The problem is that you have a matrix. You have a linear set of equations, okay, P, X, okay, but you have here some noise. If you don't have the noise, you can solve this. If you have the noise, you have a problem that is not solvable even with a quantum computer. This is a problem in which those 2 protocols is based, and then you have other digital signature protocol based on hash functions that we believe that are secure against quantum computers too. So those are the 2 solutions for the threat of quantum computers: quantum key distribution and post-quantum cryptography. In quantum key distribution, the security is based on the laws of quantum mechanics. So at a theoretical level, it is impossible to break because it will require the built-in laws of physics, but it requires expensive, nowadays, specialized devices. In the other side, you have post-quantum cryptography. This security at a theoretical level is not proven, so it's based on the experience, but it does not require specialized devices. So one idea that people have is maybe hybridize QKD and PQC somehow can give you the best of QKD and the best of PQC. Okay. But this, let's say, transition to quantum resistant cryptography should be done fast, okay? Because nowadays we have an attack, a quantum attack, let's say, which is called the harvest now, decrypt later attack. the idea is to intercept the communications in the present. Nowadays, you store them, and when a quantum computer for a cryptographically relevant quantum computer is developed, then you decrypt the information. Okay. So there is, let's say, two timelines here: the timeline of this attack and the timeline of the transition to quantum-resistant telecommunications. Okay. So in the first scenario, the time to a quantum computer is bigger than the time to do this transition. So we are okay. But in this other scenario, we are not so good. Okay. And this Q day, this day in which there will be a quantum, a cryptographically relevant quantum computer, we don't know the date, obviously, but more or less, the surveys say that will be between these years. So, and this transition is very complex. Okay? So it's a race. How can we do hybrid keys? Very easy. You have some methods that are recommended by NIST. The XOR, you XOR some keys, you obtain a key that is secure as long as one of the component keys remains secure. Or, for example, you can use a key extraction process. For example, this one, which is essentially to concatenate hash functions. Okay. So this is one important trend, let's say, in cryptography, to use hybrid cryptographic material. So you are not putting all your eggs in the same basket. You distribute a little bit the risks. Okay. So how can you implement this in the SDN model? How can you hybridize to create these hybrid keys in the SDN model? And this is one use case that we have in this project, the QB project, which is essentially through this hybridization module. Okay. Remember that in the SDN node, you have the QKD modules that talk with the local KMS, and also they change information with the agent. This is not the agent, sorry, this is not the agent of the network. It's a proxy agent that manages the hybridization module. Then this is more or less the local KMS. Okay, I name it here agent because of the nomenclature of the project. Okay, but this is more the local KMS. Okay, inside this structure. So you can add this hybridization module that establishes a post-quantum connection through, for example, the scheme to other node. You have obviously the quantum channel, and then through 004, the hybridization module, get keys from the QKD module. He gets keys from this post-quantum connection. They hybridize the keys and then forward the keys through 004, such as a big QKD/PQC module. Okay, this is kind of a big black box for this proxy agent, and this guy gets keys from this hybridization module. So as you see, it's very easy to implement in this SDN architecture. This module, you can work always with standardized interfaces. This module combines key, and you can say if they combine key, if they use one key, another. I mean, you can configure a lot this module, and also it manages the key sizes depending on the hybridization method chosen. Okay. The idea here is that the combined key, if generated, will be always at the maximum level of security, and they offer you not only security but also continuity of service. If, for example, there is an eavesdropper here, the hybridization module will give you key if you can establish a post-quantum connection. Or, for example, if some person discover an algorithm, a quantum algorithm that breaks this post-quantum method, you can eliminate this method to switch to another method, or only use this quantum channel. So this gives you a continuity of service. Okay, this hybridization model. This is more or less how the algorithm, how the flow, the information flow works. You have here the QKDs. They are generating key always. Okay, so at some point, the proxy agent requests through 004, through this interface, key to the hybridization module from Alice's side and from Bob's side. This implies that the agents, the SDN agents and the SDN controllers, they have done their work. So they request key. The hybridization module requests key to the QKD modules, and they establish a post-quantum agreement. They obtain key and they combine the key and then return the key to the proxy agent. So this is more or less the workflow, okay, of this hybridization model. And this is integrated in this architecture, which is the architecture of a single IPsec tunnel here between two nodes. So you see that reality is more complex than the theory, but what are you seeing here is the important thing is that this is the hybridization model. Okay, the network agent talks to this guy. Okay, but not for the key. I mean, because this is the agent of the network, and he doesn't want the key. He wants to establish the connection with other agent. So he talks not with the key, but with other things. This is connected to some key consumer. We don't care. And you have the QKD module that connects here. The agent creates the IPsec tunnel. Okay, gives the order to create the IPsec tunnel, which is the tunnel in which that uses the hybrid key to create a secure connection between the nodes. IPsec is a collection of protocols, okay, for security in the internet protocol. And then also you have this module is called CSIPs, and you have here an attestation agent that watches if all the software that is running here is the authentic software. Okay, if this attestation agent talks with the trust manager, which is in the controller, and if something goes wrong, the trust manager say, okay, this node is corrupted, for example, it's not the golden values, let's say, of this node are not correct, so drop the tunnel, for example. And this is the CSIPs, okay? This is in charge of the connection, and then you have, because this is a use case on virtual networks. This is a switch, and you have different pods in which you have, for example, different virtual machines running. Okay. This is the other side, and here you have, in a centralized way, the controller. You have the controller of these guys and the controller of the network. And this is the picture of all the use case. You have a lot of CSIPs. This is the CSIPs, okay? You have a lot of these connected to the trust manager, the controller, and each one has the attestation and the agent, hybridization module. You establish the IPsec here, and you have the post-quantum connection and the quantum link. So this is one use case that we are running on the network. How to hybridize, how to include hybridization in telecommunication environments. Do you have some question about this? Yeah.
I understand that this is proof of principle, but is there any benefit to actually merging those two? Because they give you the worst of both worlds and the speed of you're doing one bit operation, so XOR, and then the limited it basically reduces you to most of them in terms of security, right?
I mean, you're not limited by the post-quantum because if for example, if the key of this module, for example, if this key is corrupted, if this key is okay, you are okay. I mean, you have if both keys fail, then you have problems. But if one fails, you don't care.
The question is actually, if your using QKD is actually faster and you trust the QKD system, if you're spending so much in one structure, then why use post-quantum?
You cannot use
slow down.
No, I mean, yeah, if you're trusting this because this guy is giving you a lot of key, for example, or whatever, you can use only this module. I mean, you are not limited by this. You can configure the hybrid module to work as you want. So you can say, okay, don't do post-quantum because I cannot connect, it's very low, drop it. Okay. So you have flexibility there. But this is not the case because when you establish an IMPSEC tunnel, you establish one session and you use the same key for all the session. So I mean, this module and this post-quantum key.
We can use the QKD as a seed for IMPSEC. So
yeah.
We can use CAM as an authenticator before using QKD. Using it in a hybrid with QKD is kind of confusing, but you're using very extra resources.
Yeah.
You have the same level of security.
No, you don't have the same level of security because, for example, if for example this algorithm is compromised.
In information security, it's a standard that if you are using security software, you have to blindly trust that it is. Like if I'm using this laptop, I trust all the software are secure.
Yeah.
So then I don't need to.
Yeah, but I mean, I don't know if maybe we can talk later. Okay. More questions? Okay. So this is other different use case, which is called the law for interception, which is related to law for interception, and I put this use case in my presentation because it's another case of using hybrid cryptography, but without hybridization. What is the idea? Here, there is something called, I don't know if you are familiarized with this, law for interception. I mean, this is not quantum. Huh? This is only the introduction. This is a standard. They have the standard. This is an HC standard you have here, okay? And this is a standard for when some law enforcement agencies have to interfere with the communication legally, and you want to extract information about the communication and about the network and the communication that has been done, okay? So this is the standard, and essentially the idea is that you have two domains, the RIA domains, which is the law enforcement agency domain, it is typically, I don't know, the police, for example, and you have the CSP domain, which is the communication service provider domain, which is the telecommunication, provider. So the idea is that if this administration function gives the order, then it triggers the administration function inside the CSP domain, and then it triggers all the things necessary to intercept a communication. So this communication is essentially intercepted. You can extract some network information apart of the message, and then through this law for interception validation function, you send this to RIA domain, to the police. Okay, I'm not going to go into details because it's not important. Okay, the idea here is that how we can transform this to a quantum-resistant law for interception. One possibility is to say, okay, so I do QKD in all parts, and that's the point. No, because for example, in the CSP domain, it's impossible to put QKDs because these CSP domain are essentially our communications, mobile phones, computers, and so on. So you cannot put QKD in everything there. Okay. And well, they are not directly those devices, but are the devices that the communication service provider have to manage all the things. Okay? But in any case, you cannot put QKD here because there are a lot of, it's very complex and there are a lot of stuff going on here. So the idea is, okay, I have those two domains. I will protect the CSP domain and the RIA domain with QKD, for example, because it's a critical communication, because here goes the communication, the critical communication from the interception to the RIA domain. So I have to be sure that this is very secure. So I use QKD there. And then inside the CSP domain and also inside the RIA domain, I use post-quantum cryptography. Why? Because it's very easy to implement. Very easy to implement. It's not very easy to implement, but it's easier to implement than QKD. Okay. So you have here the paper if you want to check it. Okay. Other use case that this has not been running in properly in MadQCI, but this is not a problem because it's been proven by Indra, okay, in a laboratory. Other possible use case is, for example, to use QKD for more data ciphering, to do quantum digital signatures. A digital signature, okay, is a set of three algorithms: the key generation, the sign algorithm, and the verification algorithm. And the idea is that those three algorithms, this digital signature protocol, gives me the ability to sign a message. And to sign a message means to have those three properties: authenticity, integrity, and non-repudiation. Authenticity is to ensure that the message comes from me and not from other guy. Okay. Integrity is to prove that the message has not been modified during the way. And non-repudiation is the ability to that if I sign a message, I cannot say that I didn't sign the message. Those three properties are the properties of a digital signature, and because of non-repudiation, you need an asymmetry there. You need a way to distinguish Alice and Bob, because if I do a digital signature with a symmetric key, then how can I create a method in which I prove that it was me, the part that signed, and not you, because the key is the same. So in principle, you need asymmetric cryptography to do digital signatures, but there is a method to do digital signatures using quantum keys, QKD. Okay. And the idea is, well, this is called quantum digital signature, and the idea is that you have a protocol that has two phases: the distribution phase and the messaging phase. In the distribution phase, you, establishes secret keys between the first verifier, Bob, and the second verifier, Charlie. Okay, those keys are divided by blocks, and then those blocks are shared between Bob and Charlie, that are the two verifiers. This is K prime. Those K primes are the blocks, the random blocks that are shared between the two verifiers. So the idea is, this is the protocol, okay? So you have a message, Aris have a message, she has a message with some hash function that is quantumly secure, okay? And then Aris has the symmetric keys, they concatenate, and then through OTP, through an XOR, encrypt the hash of the message. And then she creates the partial hashes based on the block of the key, of these symmetric keys. This is the signature, and then she sends the signature together with the message to Bob, and Bob verifies the message, the signature. If at the end of the verification process you end with a valid signature, Bob gives this information to Charlie, and Charlie verifies. If you have the double verification, then you have the whole verification of the signature. If one of of this verification fails, the signature is not valid. Okay, so this is a way to implement digital signatures with quantum key distribution. So quantum keys is not only for encrypting; you can do digital signatures. Okay, we have seen that. A use case for hybridization, an use case of hybrid use of both post-quantum cryptography and QKD material. Also, we have seen how to use quantum keys to perform protocols that are not quantum key distribution. Now I'm going to show you a project that we are working on, in which we ask if it is possible to run beyond QKD protocols using commercial QKD devices. So this is the coherent one-way setup. Okay, coherent one-way is a quantum key distribution protocol in which you have a laser, an intensity modulator in the other side, and you have three states. You codify your degrees of freedom are the time beams, okay? One state is 0 in the late time beam and a coherent state in the early time beam, the opposite one, and the decoy state, which is a tensor product of both coherent states in both time beams. You give one of those three states to Bob, and Bob do this detection. You have here a beam splitter, this is the data line, and this is the monitoring line. The data line is used to extract key, essentially, and the monitoring line is used to check if there is any listening to the spine, in the channel. So, what is here? What is the idea? The idea is that if we can use this setup to run the so-called oblivious transfer, which is a beyond QKD protocol. What is oblivious transfer? Oblivious transfer is a protocol in which Alice sends a bit to Bob, okay, and Bob learns the message with probability P. But Alice ignores if Bob has learned the message or not. So it's kind of it's a key that is previous to the symmetric key, because if, for example, Alice and Bob exchange information, they can end with a symmetric key. But it's kind of a previous key, a non-symmetric key, and it's used for other applications, such as, for example, computation, shared computation, but maintaining the privacy, for example. So this is classical oblivious transfer. Okay, this is a little bit the idea of the protocol. And the question is, it is possible to do oblivious transfer with this? The answer is maybe yes. The quantum oblivious transfer version of the oblivious classical or Rabin's oblivious transfer is possible due to the existence of non-orthogonal states. So if you have this, then Bob, for example, can perform an ambiguous state discrimination through 3-operator POVM, and Bob will obtain an inconclusive probability if this overlap is real, which is given by this equation. Since the only requirement for quantum oblivious transfer is non-orthogonality, then it seems feasible to use this to execute, to use this setup to execute quantum oblivious transfer. So you have here the details. I'm not going to explain, but this is the modified protocol. What is the idea here?
Why use coherent one way when it has been shown that it's not secure?
You have one attack to coherent one way, but you can do things to do it secure.
It has been shown insecure again recently.
When? It's
like 6 months ago, tops. By Javier Faba and
Marcus Curti. Yeah. I know this attack, but maybe we can discuss later, but you can change a little bit the protocol to make it secure again. We can talk later. So yeah, if you modify this, then a little bit, in the sense that you only use those two states and you add a write puzzle right after. This is a live modification that we are seeing if it is possible to okay. We are seeing if it is possible to modify the commercial devices to run this. Then it will be possible to run a Oblivious transfer protocol. Okay. The challenge here is that it's very complex to modify commercial QKD devices because they are kind of black boxes. You cannot play with the parameters inside those devices. And how integrate this Oblivious key into SDN is another topic. Okay, because for example, you can say, okay, the KMSA have talks to the QKD device through 004 to get the symmetric key, and this goes to the consumer. Okay, but the Oblivious key is different because it's asymmetric. So you need to define what keys from Alice and what keys from Bob, and you have to synchronize this. So this maybe will require new standards or maybe modifications of the standard nowadays. We don't know still. And yeah, I'm going to talk a little bit about this, and I will end because it's too much information. And going this path towards, let's say, quantum internet, other question that we have for this quantum communication infrastructure is that if we can integrate entanglement distribution in this architecture. So this is architecture of the SDN architecture of a QKD network, of MadQCI. The question here is that, what are the difference between, I mean, you can put here quantum repeaters in general, and it will work the same, or you have to do modifications in the SDN part of the network to adapt, to be able to include quantum repeaters here. Because, for example, due to the nature of quantum of distributed entanglement, okay, distributing entanglement with quantum repeaters may be equivalent to distributing time windows, let's say, among the network nodes. So this is very similar to distributed keys, right? Well, we don't know, and we are, let's say, studying what modifications should be done in this SDN QKD paradigm to accommodate this entanglement generation. Okay. Okay, and I'm going to skip this. So I'm going to tell you a couple of use cases more, and we end. Okay. So we have seen hybrid use cases, quantum digital signature. We have also use cases that are more in the ground, let's say. For example, in this case, you have here the schema, let's say, of a use case, which is a quantum resistant video conference, which is a very simple case in the sense that you have here the different QKD vendors. Okay, they forward key to our architecture, and then through those Rhodes-Schwartz encryptors, the nodes establish a channel, a quantum communication channel, and then you can put on top an application, a consumer, which is a video call, essentially. So you can do a quantum resistant video conference with this simple use case. Also, you can perform this use case. We have performed this use case, but using different domains. Okay, so this is essentially the same, but here this connection should be done through different network domains. Okay, so you have different KMSs, different QKD vendors. We have ThinQuantum, LuxQuanta, those are KeyQuant, Quantum Opis, Jena. You have a lot of different domains, also in different countries, and yes, this is the multi-domain QKD use case. And lastly, we have an e-health use case that we run in Madrid, in which the same, you have this LuxQuanta that creates key. We use the CoolNet KMS to manage those keys, and we connect all of this to two hospitals in Madrid. The idea here is that we have different levels of requirements. For example, if one doctor wants to send a PDF to other hospital, it's very easy because it's straightforward. You encrypt the PDF, send it, and this is everything. But for example, if you want to perform a remote operation, this have more tight requirements in terms, for example, of low latency or non-denial of service. So, for example, here, hybrid approach is good because if some service, if QKD or post-quantum fails, you have the other one. So, yeah, this is all. We are those. This is the picture, and you have my so thank you very much. I don't know if you have questions or comments.
Actually, I read your reinforcement SDN network paper.
The reinforcement.
Yeah, actually, I'm doing my thesis on that direction.
Okay, I skipped because I didn't have time. So yeah, I mean, here the idea is to I skip it because it's kind of a very future use case of the network. Okay, but the idea here is to model a quantum repeater chain essentially, and to use reinforcement learning to find an entanglement swapping policy that is better than greedy. Okay, so yeah, this is essentially the idea.
There's also an overview paper with it.
Guys, no more questions? I'd like to thank the speaker again.
Thank you.